Hey everyone, it's Dr. Walker. Let's look at the first example from video 59C on work and energy. This example is a rotating rod. We have a uniform rod of length L and mass M. It's free to rotate on a frictionless pin passing through one end, right here. The rod is released from rest in the horizontal position. What is the angular speed when the rod reaches the lowest position? So the rod is rotating from up here all the way to down here. What we have to realize here is that this is a conservation of energy problem. There's no friction, there's no external forces, we have an isolated system. We have the change in kinetic energy plus the change in potential energy equals 0. We have an isolated system if we consider the system as the rod and the earth together. Let's go ahead and write the conservation of energy equation with the initial on one side and the final on the other. Notice that we're only dealing with rotational kinetic energy here. We don't have any objects moving linearly. So we can just write 1/2 I omega initial squared plus mgy initial equals 1/2 I omega final squared plus mgy final. For all conservation of energy problems, we need to define our reference level. We can consider that the motion of the object can be represented by the motion of the center of mass. The center of mass is halfway along the rod because it's a uniform rod. So what we're going to do, we're going to call the lowest point of the object the location of the center of mass when it's at its lowest position. And then over here, the initial position is going to be this much higher than the reference level of 0. It's going to be L over 2 higher. So our Y final is going to be 0. So that's why we talked about center of mass, right? Can you imagine if we had to think about the position of every single part of this object? That would not be very fun. Let's go ahead and cross out the terms that are equal to 0. It says that the rod is released from rest, so it doesn't have any initial angular speed. And we know that the final height is 0. So now what we have to do is just solve for the final angular speed, omega final. We're going to get mgy initial times 2 divided by I, and take the square root of this to get omega final by itself. So I multiplied by 2, I divided by I, then I took the square root. Now we just need to plug in the definition of the moment of inertia of this rod. It's spinning about one end, so we have to go to our table to find a moment of inertia of a rod spinning about its end. We also did this in a previous example, and we know that the answer is 1/3 ml squared. We also need to plug in our initial position. Our initial position is going to be L over 2. Let's go ahead and plug that into here. And I'm actually going to use capital M instead of lowercase m. 2mg L over 2 over 1/3 ml squared. Now let's go ahead and simplify. The m's cancel out, the 2's cancel out, one of the l's cancel out, and we get the square root of g over L. Instead of dividing by 1/3, we'll multiply by the reciprocal. So the square root of 3g over L is our answer for this first part. Let's look at part B. Here, we want to find the angular speed when the rod makes an angle of 45 degrees with the vertical. So the rod is coming down. It's making an angle of 45 degrees here with the vertical. and we want to know what is the speed over here. We can set up conservation of energy again. We need to define the lowest position. We're going to define it relative to the center of mass of the rod, which is still at the center. So right here, if we draw a horizontal line, this is going to be the lowest position, the y equals 0 level. So we need to figure out what is the initial height. It's not going to be L over 2 relative to our 0 level anymore. But we know that the center of mass is halfway along the rod, so the hypotenuse here is L over 2, this triangle that we have formed. So the initial height is going to be the hypotenuse times the cosine of 45. We can rewrite this, since we know cosine of 45 is square root of 2 over 2. We can rewrite this as square root of 2 over 4L. Now let's set up conservation of energy. Just like in the previous part, let's go ahead and write Kr plus UGI equals KF, KRF. This is initial here, this is final here. I'm just writing out the terms so I can cancel out what's equal to 0 before spelling out each term. We know that our final potential energy is 0, since y final is 0. And we know our initial rotational kinetic is 0 because it starts from rest. So we're going to have mgy initial equals 1/2 I omega final squared, just like in the previous part. And now we can go ahead and solve for omega final squared, just like before. It's going to be 2 over I mgy initial, I like to use a capital M, gy initial, take the square root, and go ahead and plug in everything that we know. We know that it's still rotating about its end, so the moment of inertia is still 1/3 ml squared, just like in the previous part. So we're going to have 2m over 1/3 ml squared g, and then our y initial is going to be square root of 2 over 4L. Let's go ahead and simplify. We're going to cancel out the m's, cancel out one of the l's. We can rewrite this again here. Omega f equals square root. Cancel out a 2 here, and bring this 1/3 up to the numerator by multiplying by the reciprocal. So we're going to have 3g square root of 2 over 2L. If we just keep the 3g over L in the square root, 3g over L, so it's just like the previous part, and we take the square root of 2 over 2, it's going to give us 0.841. So we can see that when it makes a 45-degree angle, the angular speed is about 84% of its angular speed when it reaches that vertical position.